In this video, we're going to be looking at volumes of revolutions. We have explicit formulas for finding volumes of these general shapes. The first shape, a right cylinder, we know to find the volume is pi r squared h. The next figure, we know to find the volume of this rectangular prism, we would have length times width times height. But what if we have an irregular shaped object? Something that may have been created by a lathe. Let's see if we can develop a technique that we could use to find the volume of an irregular shaped object. Here, think of this as a loaf of bread. If we're going to try to find the volume of this loaf of bread, we're going to set this on the x-axis, and we are going to take and slice it perpendicular to the x-axis. That cross section we're going to label as A of x. That's the area of the cross section. That's where we cut the slice of bread. We open up and look at the face. For this object, we're going to be looking at the volume. The slices are going to be perpendicular to the x-axis, and we're looking for the volume from A to B. Now we can see that the cross sections of this object are going to be changing as we progress from A to B. What we're going to do is we're going to give these cross sections some widths. So just like a slice of bread, we're going to give it some width. Still, we're going to be perpendicular to the x-axis. So if we can find the area of this cross section, multiply it times its width, we would have the volume of one slice of bread. Then we could find the volume of the rest of the slices, add them up to get the total volume for the loaf of bread. Now, if we let the widths of the slice of breads get smaller and smaller and smaller, which means we're going to take the limit as n goes to infinity, we have this Riemann sum, and we're taking the limit of this Riemann sum as n goes to infinity, which should give us a good estimation. If we didn't have the limit, it would be an estimation for the volume of the loaf of bread, but if we take the limit as n goes to infinity, we're going to get the exact volume of this loaf of bread. So looking at what's in front of our summation, we have A of x sub I. That's the area of the cross section. So when we cut the loaf of bread perpendicular to the x-axis, that's what we consider A of x sub I. What is the area of that cross section? Then we're going to multiply it times a width, delta x, and this should seem very familiar because this is just like when we were finding the area under a curve. Our delta x was the width of our rectangles. Then our f of x sub I for finding area under the curve was the height of the rectangles. This one, our A of x sub I, is the area of the cross section times our delta x, which is the width of each slice of bread. Now we know this is the definition of an integral if we take the limit as n goes to infinity. So if we can find the area of the cross section, we could just integrate from A to B, that cross section, and we would find the volume of this loaf of bread. So the key in these types of problems is to be able to find the area of your cross section. And that can be the challenge at times. So this is the definition of volume. Now note, when we use the volume formula, it's important to remember that A of x is the area of a moving cross section obtained by slicing through x perpendicular to the x-axis. We can also slice perpendicular to the y-axis, and then the widths would be delta y, and we'll practice that later on. But for right now, we're going to look at our slices being perpendicular to the x-axis. Let's look at an example. Show that the volume of a sphere of radius r is, and this is an explicit formula that we have been given and that we've just accepted. This is the volume of a sphere. But let's see if we can show that this is actually the volume of the sphere. Here's our sphere. Now I'm putting the sphere on the x and y coordinate plane, where the center of the sphere is located at the origin. Now let's look at a cross section perpendicular to the x-axis. So if we took a slice at this point right here and looked at that cross section, we would see that it is a circle. So you slice the sphere, open it up and look at that cross section. That would be a circle. Now we said that if we are able to get the area of our cross section as a function of x, we should be able to find the volume of this sphere. So at this point right here, that's our x value. From our origin to this point is our x value. We are trying to determine the area of our cross section here, which is a circle. We know the area of a circle is simply pi r squared. That's how I like to start these problems. Think about your cross section. What is the formula for the cross section? And just list that. Now our goal is to get this area as a function of x. So pi is just a constant, so we need to get r in terms of x, which means for this x value right here, where I have this cross section, when I plug that value in to my area formula, it has to give me the radius of the circle for that x value. So it has to give me this radius here. That's what we're calling r. But since I have this set on a coordinate plane, do you see how we could label that as the y value? So I'm going to label this as our y value. So this distance here, this radius of this cross section, is actually y, and this distance from here to here, that's our x value. We have to come up with a relationship. Let me rewrite our area formula first. We said that instead of listing this radius in red as r, we're going to list it as y, so we'd have pi times y squared. So now our goal is to get this here in terms of x. So we need to look for a relationship in terms of x and y. And you probably see a relationship here. If we complete this triangle, this would be the radius of the sphere. So I'm going to label that as r, and let me label it as capital R, so we don't confuse that with the radius of our circle at that cross section. So I'm going to label this big R. Now we can build a relationship between x and y. We can see x squared plus y squared equals r squared. And r squared is going to be the radius of the sphere. So that's a constant. That's not going to change for any of those cross sections. If we had a cross section right here, that still when we looked at this x value and the y value, this r would still be the same. So that's always a constant. So let's replace our y squared. Here, if we solve for y squared, we would have r squared minus x squared. The area as a function of x now we can find. I'm just looking at our diagram. I do see that the radius of our sphere is labeled as lowercase r. So to keep consistent, I am going to label this lowercase r because our diagram was already labeled that way. So we'll say that's lowercase r, and also here we'll label this as lowercase r since our diagram is already listed that way. Now back to replacing y in terms of x. We would have pi, and we're going to substitute r squared minus x squared in for y squared. We now have the area of our cross section as a function of x. Remember, we said that if we can find the area of the cross section times our delta x, and we take the limit as n goes to infinity, we said this is equivalent to the integral from a to b of our a of x dx. So now we can write this as an integral. We have from negative r to r. So negative r to r. And our a of x is here, so we're going to plug in pi times r squared minus x squared. And that's our area of each cross section. And then we would multiply that by dx, or put it in differential form. So there's our integral. Since this is symmetrical, I'm going to rewrite this from 0 to r times 2. If I find the volume of this half of the sphere and then just multiply that times 2, that will give me the volume of the entire sphere. So I'm just going to go from 0 to r, and then I'm going to bring the pi out front also. So we would have r squared minus x squared dx. And remember, little r is just a constant when we go to find the antiderivative. So now we'll find the antiderivative, which would be xr squared minus x cubed over 3. And we're evaluating this from 0 to r. 2 pi. Now we're going to replace all the x's with r's, so we'd have r cubed minus r cubed over 3. If we get a common denominator, we would have 3r cubed minus r cubed over 3, which gives us 2 pi times 2r cubed over 3, which is 4 pi r cubed all over 3. And you can see that 4/3 pi r cubed, 4/3 pi r cubed. We've shown that the volume of the sphere is 4 pi r cubed over 3. Here's another example. Find the volume of the solid obtained by rotating about the x-axis the region under the curve of y equals the square root of x from 0 to 1. Here is the curve of y equals the square root of x from 0 to 1. If we were to rotate this around the x-axis, we would get a shape that looks something like this. We're trying to find the volume of this solid. Now what we are actually doing is, if we take and find this cross section that's perpendicular to the x-axis, and then we're going to rotate that around the x-axis, that would give us the volume of just that piece of our object. Now, if we rotate that rectangle around the x-axis, it's going to end up looking like, I think about a hockey puck. It's going to look like this, where this would be R. Now our cross section is a circle, so we'd simply have pi r squared. So do you see that this is what's being rotated here? We're going to give it a little bit thickness. That's the width of our rectangle there, giving it a little bit of thickness. But this here is the radius of our circle. We're trying to find the area of this cross section as a function of x. The cross section is simply pi r squared. We need to be able to find how to get the radius at this x value to be this length right here. And we can see that, well, that's just plugging that x value into the function. That would give us that radius. So to get the radius of any circle, we would simply plug in the function. If we look at the Riemann sum for this, we would have pi times our f of x squared times our delta x. So if we take I equals 1 to n and then take the limit as n goes to infinity, that would find the volume of that shape. Written as an integral, we would have from a to b pi f of x squared dx. So that gives us a general formula to find the volume of this irregular shaped object by taking the integral. Now our integral would be going from 0 to 1, and we said we're going to take pi, that's a constant, so let's pull that out front. Now the function squared, our function is the square root of x, so we'd have the square root of x squared dx. This expression will find the volume of this irregular shaped object. This simplifies into x dx. So if we take the antiderivative, we would get x squared over 2 evaluated from 0 to 1. So using the fundamental theorem, we end up with pi times 1/2, or pi over 2, would be the volume. Now our units, since we're talking about volume, would be cubed. So there's the volume of this object here. So in general, if we're rotating some function around an axis, the x-axis, we can generalize our formula to this. Now this is where I say, if I said previously that if we draw in our representative rectangle, it will indicate to us if we're going to be working in functions of x or in functions of y, because we could rotate this around the y-axis also. In that case, we would put our rectangles horizontal to the x-axis, and the width would be then delta y instead of delta x. And if it's delta y, we have to have functions of y. And we'll try one of those where we rotate it around the y-axis. And there's what the figure would look like if we rotate that around our x-axis. Find the volume of the solid obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0 about the y-axis. It is important to draw in each one of these boundaries. Here is y equals x cubed. This would continue on down in this direction. So there's our y equals x cubed. Let's graph y equals 8. That's a horizontal line. So there's y equals 8. Then we have x equals 0. So that's a vertical line at 0. So we can see the area that's enclosed by those three boundaries. That area that's enclosed is right here. That's the area that we're talking about. Now we're going to rotate this area around the y-axis. This time our rectangles, I'm going to draw a representative rectangle, would look like this. Our rectangles must be perpendicular to the axis of rotation. What I mean by that, if we're rotating around the y-axis, this is perpendicular to the y-axis. If I'm rotating around the x-axis, this rectangle is perpendicular to the x-axis. So in this case, our rectangle needs to be perpendicular to the y-axis. And then if I label the width, we can see the width is along the y-axis, so it would be delta y. My functions need to be, because we have delta y, in function, it has to be a function of y. If we solve y equals x cubed, for x we would get the cube root of y. There I have a function of y. Now the area that we're going to be looking for is going to be a function of y. We know the cross section, when we rotate that rectangle around the y-axis, it's going to be a circle. That cross section would be. This would be the radius. Area of a circle, pi r squared. We have to now get r in terms of y. If we look at our radius here, that's the height of the function in terms of y. That would give us this x value, because we have x equals the cube root of y. So if I plug in this y value right here, it looks like it's about 4.2 or something. If I plug that into here, I would get this x value, which gives me the height of that rectangle. So the radius of that circle would be the cube root of y squared. So we're just replacing r in terms of y. And again, this is the challenging part right here. Once we have that, we can set up our integral. Now our integral is going to be going from, if we drew in all of the rectangles and did our Riemann sum, we would be starting at 0 here, and we'd be going all the way up here, and the last rectangle would be up here at y equals 8. So we're going from y equals 0 to y equals 8. And then our area, I'm going to pull the pi out front, and I'm going to rewrite this as y to the 2/3 power, and then times our dy. And there's our integral to find the volume. So finding the antiderivative, we're going to add 1. So we'd have y to the 5/3. Dividing by 5/3 is the same as multiplying by 3/5. We're going to evaluate this from 0 to 8. Which gives us pi. It's 3/5. We could pull that 3/5 out as a constant. 5/8 minus 3/5, 0 to the 5/3. This term goes to 0. And here, the cube root of 8 is 2. 2 to the 5th is 32. So we would have 32 times 3 times our pi all over 5 units cubed. That's the volume. And let me try to draw in what our figure looks like here. We would have, let's see, 1, 2, 3, 4, 1, 2, 3, 4. We'd be going back out to here. And so if we rotate this around the y-axis, we would get this figure here. We just found the volume of this. And that's a solid. So this is, it's not like a bowl or anything. This is a solid inside and out. Find the volume of a region enclosed by y equals x and y equals x squared, rotated about the x-axis. This problem is going to be a little bit different. And let me start out by drawing what this shape would look like. If we rotated this, we would have a shape that looks something like this. Now notice, for this x value here, if we drew in a rectangle, this is going to have a hole in that center of rotation. We're only going to be rotating this much of the rectangle around the x-axis. So we would get a shape that looked like this now, because we're going to have a hole in that center of rotation. So in our example, the x-axis would be here. And this little piece here, I would represent by this rectangle right here. This is what we're rotating around the x-axis to create this washer. Now the last technique did not have a hole in the center of rotation, and we called that the disk method. So if we have just a solid disk like this in the previous examples, this is considered to be using the disk method, and we saw that we just use this as this would be our formula for finding the volume of that disk rotated around an axis, the entire object. But now this washer method, we see that we have a radius going all the way out to here, but then we have to subtract off the radius of this small circle to here. How do we find the volume of this object? Well, we'd have pi, and let's call this big R squared. That would find the volume of the entire disk. But we are going to subtract out the volume of the smaller disk. See, we're going to subtract this piece out. We're going to take that away. Now, looking at what our area of our cross section would look like, we'd have pi. Now, going from here to all the way up here, now let's go back to our diagram. That's going from here all the way up to here. So that would be found by taking the top function. And the top function would be our y equals x. So we would have x squared, pi r squared, but we're replacing r, big R, with x. Now to find this radius here, what we're actually finding is this distance. That's what we are subtracting off. So that would be this here. We know that would be the other function, the bottom function. So we'd have pi, and then we're going to replace that with x squared. That's just replacing r, and then we still have to square it. So our integral would look like we have to go from 0, x equals 0, to where these intersect. Let me get rid of some of the lines here. So if we found where these intersect, we could set them equal to each other. X equals x squared minus x equals 0. We could factor this, and we would see x equals 0, x equals 1. So this does intersect at 1. So we would be going from 0 to 1. And now here we have our area as a function of x. I could factor out a pi. So we would have pi times x squared minus x to the 4th dx. And this would calculate the volume. Antiderivative, x cubed over 3 minus x to the 5th over 5, evaluated from 0 to 1. So that would give us 1 cubed over 3 minus 1 to the 5th over 5 minus 0. So this would be, and I have to bring this pi also. So we would have 2 pi all over 15, and our units would be cubed. So that would be our volume. So that's called the washer method. When we rotate around an axis, if there's a hole within that rotation, we use the washer method. And I like to think about it as pi times big R squared minus pi times little r squared. We subtract out that centerpiece, that hole, which makes it the washer method. Find the volume of the solid obtained by rotating the region enclosed by y equals x and y equals x squared about the line y equals 2. When we are doing a problem where we're not rotating around the x-axis or the y-axis, if we will draw the graph first and where the axis of rotation is, we can reason through the problem much easier. So let's draw our graph first of all. We have y equals x and we have x squared. I'm going to eliminate the part of the graph that's not in the intersection of these two. So we can eliminate these pieces of the graph. This is the intersection. That's what we're going to be rotating around the line y equals 2. We know that this point right here, the point of intersection, if we solved again for this equation, we would see, we get just like in the last problem, the points of intersection, x equals 0, x equals 1. But we're rotating this around this line, x equals 2. Now it's really important to remember what everything represents in our equations. We know that we're going to have a hole in the axis of rotation. Here I'm going to draw in a representative rectangle, and I can see the width is delta y. And remember, my rectangle has to be perpendicular to the axis of rotation. For this problem, we're going to find the volume of the solid obtained by rotating the region enclosed by y equals x squared about the line y equals 2. Let's draw a picture of this region that we're rotating. Now y equals x, that's a straight line through the origin, and y equals x squared is a parabola. The intersection you can see is right in here. So I'm going to eliminate the piece of the graphs that are not part of that intersection. This is all we're concerned with. Let me see if I can get rid of those. If we found the point of intersection, it would be x equals 0, x equals 1. And we are rotating this around y equals 2. So here's y equals 2. Now when we rotate this, we will have a hole in the center of rotation. So we're going to use the washer method. Let's draw a representative rectangle. My rectangle needs to be perpendicular to the axis of rotation. So the width would be a delta x. The width of this rectangle would be delta x. So that tells me I have to be in terms of x. My areas have to be in terms of x. Now with the washer method, we know our formula is going to be, and I typically like to do this first. I'm using the washer method, so I know it's pi big R squared minus pi little r squared. And since we're going to be in functions of x, dx. So the area of the cross sections are going to be our pi r big R squared minus pi little r squared. Let's look at our big R. We are rotating this, and I didn't give myself quite enough room, but we're rotating this all the way around the axis here like this. And we would have a hole in that washer. Now, this is where it gets really important to understand what big R represents and little r represents. Big R is the distance from the center of rotation to the outside function. It would be to here. That's our big R. How would we represent big R? What is that length? If we said we know the top function, I'm calling this the top. This is y equals x, and this one is our y equals x squared. So we're going from the center of rotation all the way down to our x squared. If we thought about if we just plugged in this x value to our x squared function, we would get this distance right here. That's what we would get if we just plugged in x to the function x squared. It would give us that distance. We want this distance here. Let me put this in blue. We want this distance here from the center of rotation minus this distance here. So the distance here is 2, always. So we'd have 2, and then we're going to subtract off this piece to leave us the distance from the center of rotation to the outside of the function. That would give us big R. So we'd have 2 minus our x squared. That's our big R. Now we have to find little r. Little r is the distance from the center of rotation to the inner function. And I know this is getting a little messy here, but it's that distance. And again, we could find that distance by taking 2 minus this distance right in here, which is plugging this x value into the function, and the function would be x. So setting this up in our integral, we would have the integral. Now the rectangles. The rectangles are going to go from x equals 0, we're looking at the x values, to x equals 1. So we'd be going from 0 to 1. And we're just using our formula now. Pi, and our big R, 2 minus x squared squared, minus pi, and here's our little r, 2 minus x squared. And there is how we set up this integral. And this is the challenging part, getting this integral set up. Once we get this integral set up, we know how to find the antiderivatives and evaluate it. So let's evaluate this integral. We would have pi times the integral from 0 to 1. Now I'm factoring out the pi here, so we would have left 2 minus x squared squared minus 2 minus x squared. So here we would get pi times the integral from 0 to 1, 4 minus 4x squared plus x to the 4th minus 4 minus 4x plus x squared. So let's collect our like terms. We would have the integral from 0 to 1, and this 4 cancels, and we would have an x to the 4th, and we would have, this would be negative x squared minus, so we'd have 5x squareds, and then we have a plus 4x dx. So finding our antiderivative, and evaluating this from 0 to 1, we would get 1/5 minus 5/3 plus 2, and that would give us, and don't forget the pi, we would get 8 pi over 15. Here's a summary of what we've done. Here's another example. Find the volume of the solid obtained by rotating y equals x squared about the line x equals -1. Y equals x is here, and y equals x squared, and we're rotating this around x equals -1. So I do have already this piece of the function over here drawn in, but if we rotated that around, it would look like this. That's what our shape would look like. But let's just go back to what we have here as far as our function is concerned and where we are rotating it around. Now our rectangles need to be perpendicular to the axis of rotation, so that would create a delta x when we rotate this around the axis x equals -1, we would have this washer here. And I see I wrote delta x instead of delta y. We can see this should be delta y. So we have to have functions of y. We know that since we have a hole in the axis of rotation, we're going to use pi big R squared minus pi little r squared dy. Now let's just identify what r is. Big R and little r. We'll substitute in and we'll find our integral. Big R, the distance from the center of rotation to the outside function. This is critical in setting up these problems. Understand that big R is the distance from the center of rotation to the outside function. This distance from here to here, can you see for any value of big R, if we took this one, this distance is always going to be 1, and then we're going to add in our function of y. Here we'd have 1 plus, then we would have this distance, which is our function of y. So big R is going to be 1 plus. Now the outer function is this one here. That's our outer function. And that one is our x squared. Little r is the distance from the center of rotation to the inside function to get our little rectangle. We're going to subtract that off. And again, this is going to be always 1 here, and this would be our f of y. And in this case, we would have 1, and I wrote that down wrong. Let me correct that now. Here, this is not x squared. We're in functions of y. We don't want that in terms of x. So that would be, we would have to solve for x here. So we'd have the square root of y. So we have the square root of y. Now back to the inside function, that is just y equals x. So we'd have 1 plus y. Setting up our integral, I'm going to factor out the pi. So we'd have, if I factor out the pi, this becomes big R squared minus little r squared. So it's big R, 1 plus the square root of y squared minus 1 plus, this is our little r, dy. And there we have it set up. Now, y values go from here, y equals 0, up to this point of intersection here, which is 1. If we set those equations equal to each other, we would say we go from 0 to 1. And now we can find our antiderivatives. First of all, let's multiply this out. We'd have 2 square roots of y plus y minus 1 plus 2y plus y squared. We're just foiling these two quantities up here to get these here. And so if we combine like terms, we see the ones cancel. We have a y squared here, and we have a negative 2y and a plus y. Then we have plus 2 square roots of y dy. So our antiderivative, y cubed over 3 minus y squared over 2, and we could change that y to the 1/2. If we're looking for the antiderivative of y, we'd have y to the 1/2 plus 1 is 3 over 2 divided by 3 over 2. It means we're going to multiply by 2/3. So that's where I got the 4 for here. So that would give us 4/3. And we're going to evaluate this from 0 to 1. And so we would have 1/3 minus 1/2 plus 4/3. And that's going to give us our volume. And so our volume ends up being pi over 2. And that would be units cubed.